In this video, we're going to look at how we can visualize distributions of quantitative variables. So we mentioned that bar plots are appropriate for distributions of qualitative variables. Why not apply that to quantitative? Let's look at an example of basically a continuous variable, which is the gross national income per capita, and let's try plotting it with a bar plot. Okay, so notice we have a severe case of overplotting here. It's too hard to be able to distinguish any meaningful trends about this distribution. So instead of doing bar plots, we're going to have three ways that we can visualize quantitative variables. We're actually going to start with the one on the right here. We'll be starting with, the histogram here, and then we'll look at the relation, or the related idea, which is the violin plot and the box plot. These are all great options for when you have quantitative continuous variables. So let's start with histograms first. Let's go back to the same data we've been working with, which is this data about babies and their mothers' birth weights and the baby's birth weights. Suppose now I want to plot the distribution of one of these continuous quantitative variables, in this case maternal pregnancy weight. And we're going to look here at what I could do with our categories. So I could plot one bar for each integer. If I do that, again, this is what we're going to call overplotting. Yes, I've caught some information here, but it's still really hard to see overall general trends. And so what I'm going to do is actually try to use bins of integer values as a category. And now I can start to see some overall trends in the data. A side note, these are self-reported pre-pregnancy weights, okay, when we're talking about maternal pregnancy weight. So just side note about the data itself. So we're going to talk a little bit about what we can choose for our y-axis when we're creating these histograms. So to start off, on the left, you'll see my y-axis is just a count, the number of mothers that fit in each of these weight categories. But often we're interested in actually scaling this to represent a different value, which we're going to call density. So density is going to be the fraction of data points per unit of x-axis. Okay, that's a lot. So what am I saying? I want the fraction of data points per maternal pound. Why is this useful? When I convert to density, then areas here, areas of the bars, are going to represent the proportion of data points that fall in that category. Or what this is leading us towards, if those of you that have studied probability already, this is leading us towards the idea of a probability density function, which will be what we use for continuous random variables. So that's a future lesson, but that's why we're practicing right now with histograms, how we can convert the y-axis to think in terms of fraction of data points per unit of x. Python will do this for you, just adding a density flag here in the actual input for histplot. And I'll point out there's more than one way to create a histogram plot in Python right now. For this demo, I'm just showing you via Seaborn. All right, let's dive into a little bit more intuition about this density histogram idea. So in this case, what we're really doing is saying the area is a fraction of the data points. That's what it's representing. So area is representative of proportion, or as we move forward, it's going to represent probability. How do we actually come up with the scale for the y-axis? Here, notice I just have 5 data points. Let's suppose I pick bins of width 2, plop the data points into their corresponding bins. I just now need to decide how high each bin is going to be. And so what I realize is that I need the area of one rectangle to equal 1 over 5, because altogether I'm going to have 5 rectangles so that I get a total of an area of 1 under this entire histogram. So if I know each rectangle itself is representing 1 point, it needs to have an area of 1/5, and I already know that the bin width is 2. That tells me that the height for each rectangle is going to be 1/10. If I scale them this way, this becomes a density here. So a proportion of data points per unit X. And therefore, the total area under the curve is 1, and the area of a given rectangle represents the proportion of data points that fall there. So, and in this case, when I'm saying area of a given rectangle, we're really going to be looking at the area of this entire bar here. That's letting me know that I have 3 data points that fall in this region. I'm looking at the area of this bar, and it's telling me I have 2 data points that fall in that region. So let's also try this. I'm going to give us a new histogram. This is not looking at the maternal weight. We've switched. We're looking at the weights of the babies after they're born. So that's why our histogram looks slightly different. And I want you to practice how we could shift this now to a density histogram. So let's practice just converting one output here. Let's look here at this bin of weights between 110 and 115, just eyeballing that. Actually, it should be a little bit higher. It looks like it's roughly 120, maybe a little bit less than that. And total area of this bin should therefore be about 10% when I scale it, right? It's total area of this in terms of my density histogram. So therefore, the density of this bin should be 0.02. So we're going to replot this on the next page, and you're going to see I'm going to change this y-axis, and this is going to line up to 0.02. Yep, so that's what we have here. So now, let's suppose you started with the density histogram. We know the width of the bin that we're looking at here is 5. We know the height of the bar is 0.02. So now I have a question for you. Based on using just this density histogram, how many observations would you expect there to be in the bin 110 to 115, just using this info? And what are the units of the y-axis? Okay, so let's see if we put this all together. This is the density. This is the fraction of data points per unit of X. So if I take that density, 0.02, and I multiply it by the width of the bin, that's going to give me the proportion of data points that are in the bin total. So I know that that bin is representing 10% of the overall data points. And I know I have 1,174 data points. That means we would expect the number of babies' weights that fell in that bin to be around 117, which corresponds to what we started with looking at the plot. So this is just a gut check to help you get more intuition about how we convert from frequency histograms to density histograms. The units of this, again, the units of this y-axis is the proportion of data points per unit of X. In this case, our unit of X is ounces of babies. Now we can go even further, and instead of just doing a density histogram, we can visualize basically a continuous smoothing of this, which is called a density curve, or you may hear it referred to as a kernel density estimate. Seaborn will calculate these automatically for you, so we're not going to dive into the math underneath it in that much detail, but I will give you a little bit of a sense on the next page of how we're creating this smoothed curve. Just like a histogram, density curves total area must sum to 1. And so for each data point that you have, you're going to take a nice bell curve like this, squash it down so it has an area that's proportional here. So my area would be 1/5. And then I'm going to add them together to make a curve. That's a very simplistic visualization. At the end of the day, I need the area underneath the total curve to still be 1. And I want this curve to basically have peaks where my histogram has a peak and below or near 0 where my histogram doesn't have values. Okay, so when do we use a bar chart versus a histogram? They may look the same at a quick glance, but they're really measuring different things. they're giving us information about distributions, but bar charts are specifically giving me information about qualitative variables. So in this case, the bars here are going to have arbitrary but equal widths and spacings. The order is not specified unless you have an actual ordinal variable. The height of the bars is either going to be your count, right, or it'll be the proportion of individuals that fall into that category. To contrast this, let's look at a histogram. So this is the distribution of one quantitative variable. The horizontal axis is numerical, so widths do have meaning. When I'm thinking about how to interpret heights versus areas, the area of bars, especially when I've scaled my y-axis to be density, the area of the bars equals the proportion of data points in a given bin, and the height is going to measure the density. So overall, it's important to be able to distinguish when to use one of these versus the other. Now we're going to look at how we can represent distributions of quantitative variables using what are called box plots and their counterpart, which are called violin plots. So before we can show you this visualization, we need to define what are called the percentiles. In this example, I have shaded in orange the part of the histogram where 10% of the data lies. And you can see that we're going to call the 10th percentile here this exact value. It's actually 105. This is 105 ounces for the babies. And the area to the left of this 105 is 10%. The area to the right is 90%. And so we call 105 the 10th percentile. And we can calculate it with the built-in function here in NumPy. In general, this is the value such that 10% of the data values fall at or below it. There's some slight nuances and different ways that you can calculate this, but I will point out that in general, with enough data, there's pretty little differences between the various options, but there's not necessarily one unique percentile. So we are going to be using NumPy so that we all get the exact same ones because we'll be using the same definitions. So we actually have specific names for the 25th, 50th, and 75th percentiles. Those are called quartiles, and they're visualized here in our diagram by these values. So a birth weight of 108 is the 25th percentile because the area less than or equal to that is 25% of this entire histogram. The 50th percentile is another name for what we call the median, and that is going to be the point at which half the data points lie below and half lie above. And then our upper quartile or a third quartile is another name for the 75th percentile. And we often want to capture this range between the 25th and 75th percentiles. And so we give that a name, and it's called the interquartile range. So, armed with this information, we can now plot what's called a box plot. And this is going to capture those three quartiles in the basically y-axis here. So the bottom of the box is going to start at the lower quartile. Then we're going to have a line through the box at the median. The top of the box will be at the third quartile. And then we're going to extend out these bars that look kind of like whiskers. And the way we've defined this is it's a parameter you can actually decide on and input when you create your box plot, but a common convention is to take 1.5 times your IQR, so 1.5 times this length of the box here, and go out until the furthest data point in your set that is within that range. So in this case, it looks like we have a data point right at the 1.5 times the IQR. But you'll notice our lower level doesn't go out quite as far. So 1.5 times IQR would have probably extended down here. Oh, well, maybe not quite that far to scale, but roughly 1.5 times of it, right? It's gonna extend a little bit further. And we didn't have any data point that went out to the very furthest range here. So the whisker is gonna end right here, which means that's our last data point in the set within that range. Anything outside of that is defined as an outlier. And this is really an arbitrary definition because we just took 1.5 times the IQR. But we do use it as a nice visual. We actually plot them as dots here or diamonds in this picture so that you get a sense of how many, quote, outliers might be in your data. Feel free to adjust your definition as to whether or not it's actually an outlier, depending on your own context of the data. Again, this is just arbitrary, but this is the default of how it's plotted in the box plot functionality built into Seaborn. I will point out with box plots, this width doesn't encode anything. And you can rotate these box plots so that they're going horizontally if you would prefer. So there's really some options here. And this is just recapping what I put on the previous page. We're looking now at different quantitative variable. We're looking at the birth weight of the babies as opposed to the previous page when I was looking at the maternal pregnancy weight. And then this is just showing you underneath the hood how you could calculate these percentiles yourself using built-in NumPy functions, and basically just pointing out these 3 values are going to correspond to the bottom part of the box, the line that goes through it, and then the top part. So box plots are helpful in helping us see where the majority of the data lies, but it doesn't give us any intuition as to the actual shape of the histogram or the corresponding density curve. So to address that, we can actually combine the idea of a box plot with the idea of a density curve. So if you recall, in our previous video, we have a density curve that's giving you probabilities at different points. And to create a violin plot, you're basically just going to turn that on its side here. And for symmetry's purposes, we just do it both sides, like this. Now, to also include information about your quartiles, we basically take this box plot here and imagine just smushing it this way and just encode this information. That's what's right there. So this top and bottom correspond to the top and bottom of the box, and you'll see a tiny little dot in the middle that corresponds to the median. If that's a little too hard to read, because you also lose outlier information there, you can do a box plot and violin plot all together. So that's what you see here. And that kind of is the best of all these worlds, because I have now the density curve. I have information that gives me the sense about where the majority of the data lies, but I also can visualize the outliers on here as well. So we're going to play a lot more with these throughout the semester, depending on the type of data that we're analyzing. But this was a good start to the different options that we have for visualizing quantitative data. And if you want to see this in our notebook, all of these functions and things that I plotted in here are available in the visualization notebook if you just scroll to visualizing quantitative variables and scroll down to the box plot and violin plot sections.